Hello, welcome to day 9 of Advent of Code 2022. Rope bridge. This rope bridge creaks as you walk along it. Correct. You aren't sure how old it is or whether it can even support your weight. It seems to support the elves just fine though. The bridge spans a gorge which was carved out by the massive river far below you. You step carefully. As you do, the ropes stretch and twist. You decide to distract yourself by modeling rope physics. Maybe you can even figure out where not to step. Consider a rope with a knot at each end. These knots mark the head and the tail of the rope. If the head moves far enough away from the tail is pulled toward the head. Due to nebulous reasoning involving plank lengths, you should be able to model the positions of the knots on a two-dimensional grid. Then by following a hypothetical series of motion, your puzzle input for the head, you can determine how the tail will move. Due to the aforementioned plank lengths, the rope must be quite short. In fact, the head, H, and tail, T, must always be touching, diagonally adjacent, and even overlapping. Both count as touching. Okay. Head covers tail. If the head is ever two steps directly up, down, left, or right from the tail must also move one step in that direction so it remained close enough. Otherwise, if the head and tail aren't touching and aren't in the same row or column, the tail always moves one step diagonally to keep up. You just need to work out where the tail goes as the head follows a series of motions. Assume the head and the tail both start at the same position, overlapping, for example. This series of motions moves the head right 4 steps, then up 4 steps, then left 3 steps, then down 1 step, and so on. After each step, you'll need to update the position of the tail if the step means the head is no longer adjacent to the tail. Visually, these motions occur as follows. S marks the starting position as a reference point. H covers T and S. T covers S. Now the tail would make this diagonal move here, right? Yes. Now the T would move diagonally again. T would move diagonal. But the head moves again first, so the T won't do that. It will just stay. And now the head moves and the T moves in the same direction. After simulating the rope, you can count up all of the positions the tail visited at least once. In this diagram, S again marks the start. The following after the rope, you can count up all the positions tail visited at least once. In this diagram, S again marks the starting position which the tail also visited, and hash marks the other position the tail visited. So there are 13 positions. How many positions does the tail of the rope visit at least once? Okay. So let's check how our input looks. Yes, okay, as expected. So we don't really care. We don't really care in where we start, because we only need to count the unique positions anyhow. So to keep this class, to keep track of the positions, I would set up a vector class, vector 2D, 2D, val x, int val y, int. We'll set up a difference calculation. Well, how do they calculate the distance? Let's say fun adjacent. There we put in another b, which is a vector, and then we have operator plus operator fun plus. We'll put in a vector 2D b, which is vector 2D, which returns vector x plus bx and y plus by. Also can do a minus vector x minus bx and this minus that. And we can check the adjacency, which is this minus b. And then we can check if diff and diff.x .apps absolute value is larger than 1, is smaller equal 1, and diff.y dot absolute value smaller equal 1 as well, and then we would know if those two are adjacent for our example. Okay, so I'm pretty expecting to need this. Just make this a little bit smaller, a little bit more code. We would now like to parse all the motions. Think we can set them up as constant. Maybe do that up there. So list of motions of head moves. This is a list of, we'll put in the vector 2D. And do we want to multiply it out? Give it a try. Data class, steps. There we want to put in the, we'll put in val code or direction as a chart, maybe for printing and reading it's easier. Then we have, we want to also have a vector in here. Val vector 2D, and we also want to have the length steps count with an int. And then we would say lines map this would be it.split. We'll split with a space. Parts, and then we say parts at position 0. Directions should stay at that size 0. Direction, and then create a when for the direction. We have left would mean a vector 2D -1 and 0. Up, right, down. Up would mean 0 -1. Right would mean a 1. Down would mean a 1 here. Val vector is error. And then we have the count. Count is parts at position 0, 1 to int, and then we would have the steps with the direction, then the vector, and then the count. This would then be our steps. And we now want to do one step at a time. But we, I think, start with the head, get a head start. So we will now have the var position head, and the position of head we can initialize it just with vector 2d 0 0, and we would have a var position tail, which would also be vector 2d 0 0. Or we can just say position head. And we now do the following. We do a move for the head. So for each steps, we just say for each. And we say position head plus equals with the step here, and then we do it for each for I in 0 until step.count. Step.direction. Not direction, vector. And then we check if position tail is adjacent to position head. If not, we do a move. And if this is not the case, then we need to calculate the tail move. And we can do this by having position head minus position tail. And we'll need to limit it. And this we will do with a function which we can call function crop to max step, where what we do here is we have our vector and we'll return a vector where we want it, the minimum value. Is there math.min? Yes, math.min -1. Oh. The -1 and the x, and math.min of those, and a 1. And this one will then limit it. I thought this is more logically. And then we would take this and say crop to max step. And I would say position tail. And we should keep a record, and I will do this as a list, although at the end we need to make it to a set. Positions tail is a list of, and we want to have the vector 2D here. And and then we would take the position tail to set size to string. And this is still not specified of being a vector. So I see still one complaint, but I can't really see it. Very good. So, part 2. A rope snaps. Suddenly the river is getting a lot closer than you remember. The bridge is still there, but some of the ropes that broke are now whipping towards you, and as you fall through the air. The ropes are moving too quickly to grab. You only have a few seconds to choose how to arch your body to avoid being hit. Fortunately, your simulation can be extended to support longer ropes. Rather than 2 knots, you now must simulate a rope consisting of 10 knots. 1 knot is still the head of the rope and moves according to the series of motions. Each knot further down the rope follows the knot in front of it using the same rules as before. Using the same series of motions as the above example, but with the knots marked H1, 2, 3, blah, blah. The motions now occur as follows. I'll start here. They sometimes cover each other, okay. Now you need to keep track of the positions. The new tail 9 visits. In this example, the tail never moves, and so it's only visits one position. However, be careful, more types of motion are possible than before, so you might want to visually compare your simulated rope to the one above. Here's a larger example. More types of motion are possible than before. This is still the old example, I would suggest. Then we have a larger example. These motions occur as follows. Individual steps are not shown. Simulate your complete series of motion on larger rope with 10 knots. How many positions does the tail of the rope visit at least once? I would say we can keep them. Most probably not gonna change anything on that. Copy our solve method. We'll copy the input. I think they told us that for this example the check is only 1, but there should be a bigger example. And this time now take this new file example2.check add, which is 36, new file .in, which would be this, and I don't really know why we had this list in the first place, but we can just call this parse input, parse moves. Good, we don't really need this as well. Yeah, now we'll need to come up with something more useful than that here. The position tail and all that stuff, that's super fine. However, we want to have a position map. Which we want to construct. I think we'll call it 0 until 10 dot associate with position head. They don't really matter. I just call this one start. And I think we can also do the record here for keep our the current position. Which just will be take the position map, values, list of it. So this should actually be solved here. The only question is, do we need do we need to keep track of the position itself, or can we just take the last element of the list? I think we can just always take the last element of the list. Yeah, we'll see. So I think that's what I now wanted to check is how they actually move. So this is already part 2. No. Here we start with part 2. Covers, so head moves, then the one moves. Yeah, so they basically all move like a snail. So we now have our counts here, but we'll now need to do this for all. So I would now say position record. Now we can iterate over all our for not in 0 until 10. I would now say position record dot at position not dot not last. Yeah. And obviously with the get value here. And I think we'll do it for 0 for now. Do it maybe for 0 outside. I think that will make sense. And we tell it that this is the last position, and we will update this one with positions, and then we will say positions dot add, and we will add positions dot last with plus the step dot vector. Positions is a mutable list. This is, I don't really want this. I want actually it dot value. This is what I want. So this is changed here, and we here then want to say that we want to check if the position not is not -1 dot last, and position current not is this one, and this we want to have the positions because we want to alter it. And then we would say if the positions of the current not, or the last position of the current not, is adjacent to the position of the previous not, or let's say is not adjacent to the position of the previous not, then we want to take the position of the current not and add positions of current node, position current node. We'll take this one here because we need it for computation last multiple times. So we'll take this one, call this current position current node. If the current position of the current node is not adjacent to the previous node, then we want to say the current position of the current node should be updated, should be moved. And we'll take the position of the previous node, then subtract the, so we get the difference, and then we want to crop this to the maximum step. And this is the movement, current node movement. And then we want to say the positions. We want to add an element, which is the current position of the current node plus the current node movement. And then we should be good to go. No, yeah, okay, no, that's fine. And there we would then say the position record of 9 dot get value of 9 to set size and so on. Yeah, I would say we can just give it a run. Oh, I fucked this one up, sorry. P2. Seems good. Nice. So, actually, this was much faster than I expected, and also kind of liked my solution. Oh, cool. Yeah, thank you for joining in. Have a nice day and see you tomorrow. Hopefully with an example that works as smoothly as today.